Well, this is the last video on chapter 2. I'm dealing with periodic table, atomic structure, isotopes, and now we're looking at molar mass calculations or applying it to atomic mass. In the last video, we saw that with any particular element, there's a measurement in the box that represents this element in the periodic table. We know the 17 is the number of protons of the atomic number here for chlorine, and the whole number within the periodic table, the whole number for the box of the element, is always the number of protons or atomic number. It's kind of, again, your identity. But the one that has a decimal point we've learned in class is a measurement, and it's no different here. Now, the measurement they use is for the atom, or we'll say microscale, is AMU, but we can often say for 1 mole, a great number of them, 6.02 times 10 to the 23rd, this will represent grams. So when we make that adjustment from micro to macro, think of this as representing 1 mole, a pile. And its average weight in grams is 35.45 grams because you don't have just one isotope. In many cases, you have, in this case, we have the isotope Cl35, which has our 17 protons plus our 18 neutrons, but we also have another one, Cl37. Cl37, we say, oh, that is an isotope that has it has a 17 protons, has to be chlorine. But in this case, then it has 20 neutrons. And instruments have to be used to measure how much of each you have in a pile, in a sampling of chlorine. And so from that, you can say, oh, the instrument tells us how much of this we have. We know its exact weight. So it won't be exactly 35, but it'll be very, very close. And it won't be exactly 37. It'll be very, very close. So we did that calculation in the last video. But now we need to move on to this concept of mole. How do we use that in chemistry to kind of get us from discussion of the mole level? How can we use that to always be thinking in terms of grams? It is a tool. This is our kind of leverage point, molar mass, the mass of 1 mole. Mole is just, please, a chemist dozen. It just represents a big number, like a ream of paper is 500 sheets. I guess a case is 24 cans, a dozen is 12, and a pair is 2. A chemist thinks of a mole in the same way. A mole is just a very big number, 6.02 times 10 to the 23rd. That's just our addition to a ratio. It's called the Avogadro's number, and it's known precisely now, or became more precisely. It's got more precision we could add to it, but 6.02214154 is the getting closer to the exact number of carbon atoms in one mole of carbon-12. So here's the definition again. A mole is a unit that represents the same number of particles that are in carbon that are I guess in 12 grams of carbon-12. 12 grams of carbon-12 has 6.02 times 10 to the 23rd carbon atoms in it, and we're getting more precise every year. We can apply that past carbon and say a mole is always going to have that Avogadro's number. It's very large, so just to kind of think of the amount of water in the world's oceans in liters, we're still above that point in the number. We're 2 places past that. Population on Earth is way down here. You're 3 billion, and we're climbing. That's old, but that gives you an idea how large this number is. Now let's use it. So mole equals, I guess, again, a 6.02 times 10 to the 23rd, we'll say roughly, of anything. It's our dozen. And the atomic mass is the mass of 1 mole of whatever that atom is, whatever we're speaking of. So the atomic mass is the mass of 1 mole of that, shouldn't say atom, but of all those atoms together. So we can do a couple things. We can always take our grams and convert to number of moles. We can always take moles and convert to number of grams. So it's, again, a conversion. We can use our molar mass, or we'll hear it sometimes as atomic mass, as a way to convert from grams to moles, or the other way. It doesn't matter. But we can also convert grams to number of atoms. We can also do that. And we'll see that. And so this section that we're in right now, the last section for Chapter 2, picks up with what you've already seen from Chapter 1 of dimensional analysis or Fence-Post calculation. So here's why we have to do this kind of math. Remember, John Dalton talks in terms of A plus B gives C, and he says you have one of these and get one of these, it'll make one of these. When you're saying one of these and one of these, you're saying numbers. So the problem is that when you walk into the lab and you're trying to do a reaction, you've got to work with mass. You can just grab a hunk of zinc here or magnesium, and you have to deal with how much do I need of the acid to react with this. You can't count the atoms, but you can take a weight. So what you'll do is take the weight and you'll convert that to number of moles. So we can do this expansion of the ratio. We know that for 1 mole of magnesium, this is the atomic mass, 24.31 grams of magnesium is what you have. But we can expand that and say, well, that's got to be equal to what I don't know is the number of moles in this over 5.657. So remember how we talked in class about how we set up the math. You can do the one that students most like to do, is expanding the ratio. I know this ratio, that's the atomic mass, the mass of 1 mole. I just don't know how many moles I have, so I'll set that over the weight that I do have. We can then determine what is the number of moles in that calculation. So I've gone ahead and shown the answer for that. This would be the answer. But we can also just, again, move a little bit past that and say, well, maybe I want to know also the number of atoms in 1 mole. Not only do I know the weight of 1 mole, but I know that 1 mole is equal to 6.02 times 10 to the 23rd. So I can further convert that if I wanted to, timesing it by the number of atoms that I know are in 1 mole. Okay, we're just going to do a couple example problems, and then we'll pick up with this in the class. So often students are asked to determine either the number of moles or number of atoms from some weight. They'll have some weight of the atoms or element. And that's going to be then probably best to use conversions along the way. So I'm going to show it that way. Please, that's kind of, again, the language of the textbooks, and you do need to learn how to sort of read it. So let's say they wanted to know what's the number of Cu atoms. Not moles. They're going past that. That's in 2.45 moles of Cu. So the first thing I tell students is sometimes maybe get a grid of where you are. So typically you're either at grams, or you're down at moles, or at number of atoms. And we'll talk more about this sort of stop along the way from moles to atoms. For right now, though, let's just think grams, moles, atoms. I'm at one of these 3 places, and I'm trying to get to the other one of the 2. So right now, I am here. So what I can say is I know for a mole of, in this case, copper, I know there's 6.02 times 10 to the 23rd atoms of copper. So I can use that conversion. This is a conversion. It gets me from moles down to atoms directly. So moles for Cu atoms. I can use this conversion along the way. I can put this into a spot, just like we talked about having the engine, the car, and the caboose being our answer, what we want. I can say I take my starting point, my engine is 2.45 moles of Cu. I put my conversion factor in. I know that I have the unit on the bottom, mole of Cu is equal to 6.02 times 10 to the 23rd. I do the math to get to what my number of atoms are, and that comes out to 1.53 copper atoms present in 2.45 moles. And again, you may have to work some math. I tell students just multiply these numbers, and whatever you get, just times it by the 10.323. So I'm going to show you that real quick on my handy-dandy calculator. We're just going to, just sometimes students don't know how to deal with this number, 6.02 times 10 to the 23rd. You can just take the 2.45, times it by 6.02. That's going to give us, okay, so why is that not working out? So I might have to change this number here. Let me try it again. 2.45 times 6.02 equals, okay, it looks like I made a mistake here. It's 14.749 that I get just by multiplying those numbers, and I can just bring this back down, times 10 to the 23rd. So I can say that is my answer for the Cu atoms. And again, this is wrong. 1.53 is not what we get. And I can report that if I wanted to. You don't have to. You could report it as 1.4749 times 10 to the 24th, because this is making the number smaller. But you can just leave it this way too. I'll accept that for your quiz or test. Let's do one more. Again, I made a mistake, so you want to adjust your notes when we take this number, 2.45 times 6.02. I've done it twice, and it seems to make sense. That's 14.749, and we just bring the times 10 to the 23rd back down. Let's try this now. Okay, 15.84 grams, so I'm at grams. That's where I'm at. I'm here. That's my engine. I have 15.84 grams. That's what I have. And they want to know the number of atoms. Okay, so this is going all the way. It's kind of going from, remember on our map we said there's grams and there's moles and there's atoms. I'm going from here all the way down. So there's going to be two conversions. One from grams to moles, the other from moles to atoms. So I'm really going to sort of set it up that way. I'm going to say I'm going to have two conversions of this 15.84 grams of calcium. Again, you say, how do you know there were these two? Again, because it told me I had grams, and I kind of put my finger on a map and say, oh, I have grams. It's not asking for number of moles. It's asking for number of atoms. So that's past moles. And I have to say, then I have two arrows, two conversions. And the first one has to be grams of calcium, gets me to moles. So we say, okay, what is the number of grams in calcium? So we can take and look at our periodic table. So I'm going to pull this out real quick. I'll just take it from the book, and you'll have your piece of paper. I have, for this, and you may not be able to see it, for calcium, it's 40.08. 40.08 grams. And you say, where'd you get that? From the periodic table. 40.08 grams for every 1 mole of calcium. But I'm not done yet. I have to say, oh, he wants number of atoms, so I know it's 6.02 times 10 to the 23rd over 1 mole of calcium. That would give me my number of calcium atoms. So let's do the math, and we're not going to worry about that 10 to the 23rd. Just going to take everything in the numerator. This is, if you need to put that over 1, that's fine. 15.84. I'm going to times it by the 6.02 times 6.02, hit equals. So what do you do with this number? Well, as soon as I have the multiplication product, now I'm just going to hit divide that by the 40.08 and hit equals. And now I have my answer, which I'm going to write it as a product of all this, is equal to 2.3, and let's go with sig figs. We had 4 here. It's always, you never limit yourself by the molar mass or the 6.02, so it's 4. So 2.379, and don't forget to bring this times 10 to the 23rd back down because you didn't add it into your calculation. Times 10 to the 23rd is our number of calcium atoms, and we can write it as calcium atoms. Maybe it'd be better to do that, calcium atoms. And we are done. Hope that helps. We'll, of course, do more in using this map, and we'll just, for now, we'll just say, hey, if I need to go from grams to atoms, we go from grams to moles to atoms. I'll work this in about what do you mean about particles. It's a more complex problem, probably best for class. But kind of use that map. I'm at grams, I need to go to atoms, I have that one step in between, I have to go to moles. And we do those 2 conversions, just like we did here. And that gets us there. Thanks. Bye-bye. See you in class.